Okay, so we have established some fundamentals with regards to the resistor and the capacitor. So let's look at combining those now. So let's look at a circuit that has a resistor and a capacitor arranged as follows. So R and C. So what do we know? Let's have a look. We've got current, we've got I coming in, let's call it I total. We have IC there. Now we know from looking at this that we can say that IT equals IC because there's nowhere else where the current is flowing. So IT equals IC. That's the first thing we can write. We also know from the potential divider circuit that we looked at previously that we can specify that this voltage across this particular impedance, this capacitor, we can find by the potential divider equation. So we can say that VC is equal to, now if we remember back to this type of circuit where we had two resistors, we said that the potential divider equation was the resistor of interest, R2, divided by the total, which is R1 plus R2, multiplied by this V, gives us this voltage across R2, VR2. Well, in order to solve this, we just do it in the same way. So we say the voltage across the capacitor is the impedance of interest, which in this case, let's just remember, we say it's XC. This is the impedance, the imaginary impedance, divided by the total. And in this case, it would be R plus XC. Now, this all looks a bit nasty because if we recall, XC is 1 divided by 2 pi FC. So the impedance of this capacitor will change with regards to frequency. Well, what we can do is divide through by XC. We end up with, so we do divide by XC, so divide top and bottom, we end up with XC divided by XC is 1, divided by, and then we have R divided by XC plus 1. And that's obviously going to all be multiplied by our V, our supply, V. Now, this is XC, which is 1 divided by 2 pi FC, so we can kind of flip the 2 pi FC back onto the top of this. So this actually ends up as follows. So we end up with, and this equation is, or rather this portion of the equation, is something that's often referred to as the transfer function. So depending upon the magnitudes that we choose for the R's and the C's, this will give us a proportion of the input voltage that gets transferred to the output, i.e. in this case the voltage across this C. So in actual fact this is an RC filter. So as we can see, as we change F, this proportion, this ratio of these impedances will change and we will get a different voltage. And in this case, if we were to plot F and VC, so this is the voltage across the capacitor, we will see that we'll get this response. This is known as the bandwidth of the filter, and we also have this 3 dB point. This is called minus 3 dB, so this is when it's 3 dB down from this max value. And sometimes in texts you will see this shown like this. So this is the H, i.e. transfer function. This is in the S domain now, so we've gone into the complex frequency domain here, and you sometimes see this expressed as follows. So what we've done is we've taken the 2 pi f and now we've replaced it with this S. Now this S is sigma plus this imaginary part, so we often say that is j omega, where omega is equal to this 2 pi f portion. Now in this case, if we're just considering the AC component, so if this were an AC signal going in, then we can largely ignore the sigma part. More on this later, but just when we're analysing these circuits in the basic form, this equation here, if you want to derive the output of a voltage at a particular frequency, then you would use the equation that I've highlighted here. If you wanted to find the absolute magnitude, we've got a difficulty here. This is what you say is the imaginary impedance, because it's formed using this capacitor, and this R is essentially a real part of the number. So this is, we could say this is 1 plus j RC. So the way to solve this, then you would have to do something like, if you look at the magnitude of h of s, then this would be 1 divided by the square root of sRC squared plus 1 squared. And there you have it. So an alternative way of looking at this, given that we know that the IC, and we also can see through Kirchhoff's voltage laws that the total voltage here must equal the sum of the voltage across the resistor plus the voltage across the capacitor. If we start writing out something like V, so this is our total V here, V, we can say is equal to VR plus VC. VC. What we can then think about is, we can say V is equal to, now if we think, we said earlier that this IT must equal this IC, so IT is IC. Well, the IT is the current that's flowing through the resistor. Now if we express this in terms of its current, we can say, okay, well, we've got R times this IT here, just leave this as VC. So we know that this IC equals the IT, so if we rewrite that again, what we'll get is RC dV dt plus VC. Now everything at the moment we're considering in the time domain. So V with respect to time, this is with respect to time, etc. Now this, solving this equation, in order to get this voltage output, we'd have to do a differential equation. However, there's this process called the Laplace Transform. I'm not going to go into too much detail about the transform itself, other than to say we transfer from the time domain to the frequency domain, or the S domain, and the best way of doing this, we often refer to transform tables. The more you do transforms, you will be able to recognize the Laplace equivalent of the time domain function in order to transform it into or between the two domains. What we can say is this section here, R in this case is going to be a constant, so we can forget about that because a constant remains a constant whether we're in the time domain or the frequency domain. But what we need to do is take the Laplace transform of the left hand side and the Laplace transform of the right hand side, and anything that is with respect to t, so this is Vt, this is all Vt, this is going to be Vt, transforms into a V sub s. So we can say that V equals, R is a constant, so we're going to keep that as a constant. C, we get C of s, and V, we'll call it Vc of s, just to differentiate, because that's the change of voltage across the cap. And this one, again, Vc of s. So now we've got a nice algebraic equation that we can manipulate. So let's do that. Let's say V sub s is equal to, this is our output. So we need to express this as a transfer function. So we've got our output divided by the input. So if we bring the v-squared across and then take this across there, we will end up with our transfer function, which is equal to, as we can see, this equation is exactly the same as the one that we previously defined. We're in the S domain here, and that's usually enough to find the output of this particular circuit.